Okay, I hope I am clearly audible and visible. This is the week 10 of the problem solving session. We have 2 more weeks to go, and no one is there yet. I can see anyone joined yet. So we'll wait for 5 to 10 more minutes for someone to join, and then we'll start with today's session. Okay. It's already 7:16 and I don't think anyone will be joining today. So I think we should start with today's session. Whoever wants to check out the classes, we'll be uploading the YouTube link. You can check from that. Okay. And if you'll be having any doubt, we have 2 more sessions. You can contact with me on the next session. Okay. So let me share the first question. Okay, so in previous class, we were left with 3 questions rather. Okay, so this is the first question for previous class. Uh, you first check out the question that is about heat exchanger. So in heat exchanger, the heat capacities are same for both hot and cold fluid. Okay, and the hot fluid is entering at 76 degrees Celsius and leaving at 47 degrees Celsius, and the cold fluid is entering at 26 degrees Celsius and is leaving at 55 degrees Celsius. So what is the effectiveness that we need to calculate? So simply we'll be using formula and we'll be calculating the effectiveness for the same. Okay, so I'll give you 2 minutes for this, and you can calculate and give me the answer. I think we should go for the solution because we have many more questions for today itself. Today we'll go on with the more problems with the topic of radiation. Okay. Um So I've already taught you the equations that will be applicable. We'll just be concentrating on problems rather. Okay, so for this question, already the heat capacities, it said that it's same, so we don't need to consider that. So for effectiveness, we need to find effectiveness. So for effectiveness of heat exchanger, we already know that it's T actual, sorry, the MCP delta T, delta T for any fluid that will be depending upon the MCP of the minimum fluid, right? That is, if either if it is hot, then we'll be considering hot fluid on the top, on the actual, and if it is MCP is minimum is of the cold fluid, then we'll be considering the actual to be of the cold fluid. So now, as it is same for both, so we'll be considering considering for the hot fluid as it is. So it will be THI minus TH naught, that is temperature difference for the hot fluid, and the maximum temperature difference. So that is THI minus TCI. So this will be so this is the actual is 76 minus 47 for the hot fluid, temperature difference of the hot fluid, inlet and outlet. And for the maximum temperature of the hot fluid is 76, and the minimum temperature, that is for the cold fluid inlet temperature, is 26 degrees Celsius. So this is 29 upon 50. So this will be 0.58. That is which of the option? This is option B. Okay. Now let us proceed for the next question. Okay. So it is said that the value of the effectiveness ranges from 0 to 1, and it increases rapidly with NTU for small values up to NTU 1.5, but rather slowly for large values. Therefore, the use of heat exchanger with large NTU, usually larger than 3, and thus the large size cannot be justified economically, obviously. And since large increase in NTU in this case corresponds to NTU is directly proportional to area, right? The area for heat exchanger. So if we will go to higher values of NTU, it will need higher heat exchange area. So obviously that won't be economical. So this statement is true, since a large increase in NTU in this case corresponds to small increase in effectiveness. Yeah, when we will go for larger values, the change in effectiveness will be very small rather, and also we'll need large heat exchange area, so that is not feasible economically. So this statement is true. And for a given NTU, the capacity ratio is C minimum upon maximum. The counterflow heat exchanger has the highest effectiveness, followed closely by cross flow with both fluid unmixed, and the lowest is for parallel flow heat exchanger. That is also true. So both of the statements are true. That means it will be option, the 11 will be option A. That is true. Right. Now for the next question. Okay. So what is it said? A shell and tube heat exchanger is given with one shell and two tube pass is used as a regenerator to preheat milk before it is pasteurized. So cold milk enters at 5 degrees Celsius, while hot milk, which has completed the pasteurization, is re-entering as hot fluid. So that is the hot fluid. So the hot fluid inlet temperature is 70 degrees Celsius. Okay. So if leaving the regenerator, the heated milk enters a second heat exchanger, which raises the temperature to 70 degrees Celsius. So the cold fluid outlet temperature is 70, inlet temperature is 5, and the cold fluid outlet is coming back again as the hot fluid inlet. So that will be the hot fluid inlet temperature will also be 70 degrees Celsius. And now a regenerator is to be used in a pasteurization process for which the flow rate of the milk is given. For both cold and hot, the flow rate will be same, mass flow rate is same, that is 5 kg per second. For this flow rate, the manufacturer of regenerator specifies an overall heat transfer coefficient as 2000 watt per meter square Kelvin. So the overall heat transfer coefficient is given, U is given. If the desired effectiveness of the regenerator is 0.5, effectiveness is also given. What is the heat transfer area that is required? Okay, so we need NTU so that we can get the heat transfer area. What is the corresponding rate of heat recovery? and the fluid outlet temperatures. Okay, so the fluid outlet temperatures we need, and the corresponding heat recovery we need. If the hot fluid is the secondary heat exchanger, hot fluid in the secondary heat exchangers derives the energy from combustion of natural gas. Okay, so what is happening here? Okay, the cold fluid is entering, it is moving out, and it is then when it is temperature is increasing, it is used for second heat exchanger for pasteurization, right? So for the second heat exchanger, natural gas is combusted, and the burner efficiency is 0.9%, and that is used as source of energy. What would be the annual savings if the energy and fuel cost associated with the installation of the regenerator? Facility operates continuously throughout the year, and the cost of natural gas is also given per megajoule. Right, and all the equations that will be required for you are also provided here for shell and tube, one shell pass, and 2, 4, and like other tube passes. So the equations are given. These equations you need to apply. Right. So for your simplification, let me draw the final, like what this means rather. Okay, so what is happening? This is one shell, 2 tube passes. So TCI, that is the cold fluid, is entering at 5 degrees Celsius, and it's leaving at some outlet temperature. So we don't know the outlet temperature yet. So it is the like, as it said, after leaving the regenerator, the heated milk enters second heat exchanger, where its temperature is raised to 70 degree. Okay, okay. So from when it is when the cold fluid is entering on the first one, it and leaving the first one, we don't know the temperature at that time. So when it is leaving the heat exchanger, we need to calculate the temperature at that point of time. And when it is entering the second heat exchanger and leaving that temperature, we know that it raises to the outlet temperature raises to 70 degrees Celsius. So this temperature we don't know, right? And when it is raised to 70 degrees Celsius, that is coming as the inlet hot fluid, that is, this is 70 degrees Celsius. And what is the outlet temperature? That is like when it is cooled, what is the outlet temperature of the hot fluid? We don't know, right? Mm, Now, so what it simplifies to? It simplifies to the TH inlet is 70 degrees Celsius, and outlet we don't know, and TC inlet is 5 degrees Celsius, and outlet we don't know, right? And MC dot is given, MH dot is also given. Both of them are 5 kg per second. And overall heat exchange area is given as 2000 watt per meter square Kelvin. Okay, and effectiveness is also given as 0.50. So let us take assumptions first. Assumptions will be, first one is negligible heat loss to surroundings, and number, this is A, this is B. B is constant properties. So these are the assumptions that we are approaching to. So first of all, what do we need to calculate? We need to calculate the outlet temperatures of the fluid and the heat transfer area. So for the heat transfer area, okay, so this equation we can apply, and for this equation we need E, and for E we can use this equation. This CR is the heat capacity ratio. So in this over here it said that heat capacity ratio is 1, right? And for that we can apply this equation. So everything is given, you can clearly apply this. and the heat recovery rate is also can also be found out by this equation, right? So everything is given for the first part, you can easily find out, and let us focus on the first part first, then we'll focus on the second part. So I'll give you 5 minutes to solve this, and like I want you, when you are even watching the recorded session, the time that is allotted to you, at that time only you finish that, because that will be helpful for your further exams, because there will be limited time slot by which you need to complete the questions. So I've explained to you what is happening over here, and now you can go for proceed for solving this. So part A you solve, then we'll discuss the part B, how to solve the part B. Okay. So let us take 5 minutes to solve this, and then we'll proceed with the solution. So I hope you have solved somewhat of your problem. So okay, so for the first part, we'll proceed with the solution. So it's already given that the capacity ratio is 1 and effectiveness is 0.50. Right. So first what we need to calculate, for A we need E, right? So E, how can we calculate? It's 2, it's not visible properly, right? So it is 2 upon epsilon 1 minus 1 plus C1 upon 1 plus CR square whole to the power half. So epsilon is 0.50. So 2 upon 0.50 minus 1 plus 1, 1 plus 1 square whole to the power half. Sorry. So this will come out to be 1.414. Okay. So I've pre-calculated, already calculated it. Now, what do we need? We need C minimum. C minimum is, we need to calculate it first. So m kg per second into m Cp delta T. So Cp is 3860 mCp. So mCp J kg joule kg per Kelvin. Joule per kg Kelvin. Okay, so this what we have calculated is 19300 watt per Kelvin. So now we can easily calculate area. So that is C mean upon U ln E minus 1 upon E plus 1 upon 1 plus capacity ratio square whole to the power half. So this will come out to be 19300 upon U is 2000 watt per Kelvin, watt per meter square Kelvin, ln 1.414 minus 1 upon 1.414 plus 1 upon 1.414. So this will come out to be 2.03 meters square. Now with epsilon is equal to 0.50, now we need to find the heat recovery rate. The heat recovery rate Q is epsilon C mean THI minus TCI. Right? Now inlet temperatures we already know. So this is 0.50 into what is this 19300 and this is 70 minus and this is 5. So this will come out to be 627,000 watt. Now we need to find the outlet temperatures. So the outlet temperature is first Tc naught by heat balance, energy balances for the cold fluid and hot fluid, we can easily calculate that. So Tci plus Q upon heat capacity. So heat capacities of both are the same. So this is 5 degrees Celsius plus 627,000 watt upon 19300 watt per Kelvin. So this will come out to be 37.5 degrees Celsius.
and TH outlet is TH inlet plus Q upon C hot fluid. Sorry, this will be minus. Just 1 second. And this will be 70 degrees Celsius plus 627,000 again upon 193 because the heat capacities are also same. 00 watt per Kelvin. So this will come out to be again 37.5 degrees Celsius. Now for part B. So we need to find the energy recovered with 90% efficiency, right? And for that, what it's asked, what would be the annual savings? So for the energy annual savings, first we need to find the an energy recovered. So for the energy recovered, we already know the heat recovery rate. So heat recovery rate is 627,000. So this will be this is watt per Kelvin. So this is watt, and we need like it said that, okay, says the amount. So we need to calculate for how many days per year. So it's for throughout the year, right? So there are 365 days for a year. So 365 days per year, and that days we need to calculate terms of what it said. Now, what would be the annual savings in fuel cost associated with installation of the regenerator? So we can convert it to per year, right? And for 365 days, 365 days, there are 365 days in a year, and in one day there are 24 hours, and there are 3600 seconds in 1 hour. So by that we can convert how many joules per year, like what is joule per second, right? So second we'll just convert it to year. So how many joule per year energy is recovered in continuous operation, we have calculated that, and for per joule it's at $0.02. Okay, so that energy what we have recovered into the cost per joule, so that will be the amount upon the efficiency. So efficiency will be 0.8. So upon the efficiency, so that will be the total annual fuel savings, right? So that you can easily calculate. So I'll give you 2 minutes to solve this. This will be the second part of the like part B of this question. You solve this and then we'll proceed with the next question. Okay. Yeah, so I think we should proceed with the solution now. So first of all, the amount of energy recovered, as I already said, we'll find that out for continuous operation over 365 days. So del E is equal to 627 triple zero watt, like we already found out here, right? Yeah. So that into so that is joule per second. So second will convert to year, right? So there are 365 days in a year, and there are 24 hours in a day, and there are 3600 second in hour. So this is converted to joule per year, right? So this is 1.98 into 10 to the power 13 joule per year. So now we need to find the savings. So the annual fuel savings is then SA is equal to del E, the total energy recovered, into CNG, that is the amount per like per joule, that is already the amount that is required, it's already given, upon the efficiency, that is 0.9. Right. So this is 1.98 into 10 to the power 13 into 0.02 into 10 to the power. This is per megajoule, 10 to the power minus 6. Right. Okay. So 10 to the power minus 6 per joule, and this is 0.9. So this will come out 440,000 dollar per year. Okay. Now let us proceed to the next question. So this is the 13th number question for the previous class. So what it said, a concentric tube of tube heat exchanger for cooling lubricating oil is comprised of three thin wall inner tube of 25 mm dia carrying water and an outer tube of 45 mm dia carrying the oil. Simple. There are two tubes. Inner diameter. This is a double pipe heat exchanger. So the inner dia is already given as 25 and outer one is 45. So the exchanger operates in counter flow with an overall heat transfer coefficient is also given, and the tabulated average properties are also given. So what we need to find out, if the outlet temperature of the oil is 60 degrees Celsius, this the hot oil is the hot fluid. So the hot fluid is in the concentric region, that annular region, and its inlet temperature is 100 degrees Celsius and outlet temperature we don't know. And the fluid like the water is the inlet is the cold fluid. This inlet temperature is 30 degrees Celsius, outlet temperature we don't know. So it's already given here. This is the equation that we are going to apply for NTU. And if the outlet temperature is of the oil is 60 degrees Celsius, outlet temperature is given as 60 degrees Celsius. Determine the total heat transfer and the outlet temperature of the water. So we can simply do the energy balances and find this out, and determine the length required for the heat exchanger. So area, if we find the area, if we find the area, then we can easily calculate the length from here, right? So you do this. I'll give you 5 minutes for solving this. I'll be here if you are having any doubt, and then we'll proceed with the solution. Okay. So it's already 5 minutes. I think we should proceed with the solution now. Mm. So the first part of the question is, for the first part, we'll take this and take this up, and for the second part, we may wait for 2 more minutes. So for the first part, it was like it is asked that total heat transfer area and the outlet temperature of water we need to calculate. So first of all, we can draw a simplified diagram. So this is TH in inlet is 100 degrees Celsius, and outlet is given as 60 degrees Celsius, and this is mass flow rate of hot fluid. This is 0.1 kg per second, and the mass flow rate of cold fluid is, this is counter flow rate, so this is 0.1 kg per second. So this is outlet, and this is inlet cold fluid. So this is 30 degrees Celsius. U is given as 60 watt per meter square Kelvin, and dia is 25 mm. So now we are assuming that negligible heat loss to the surroundings and negligible thermal resistance to the tube wall thickness. Okay, that means conduction won't be like for conduction heat loss won't be there. So now with outlet temperature as 60 degrees Celsius, from overall energy balance on the hot fluid, we can get Q. Q is mH dot Cph Thi minus Th naught. So this is 0.1 kg per second. It's already given, right? Into Cph is given as 1900 for oil, 1900, yeah, 1900 joule per kg Kelvin, and into 100 minus 60 degrees Celsius. So this is 7600 watt. Now, from energy balance on the cold fluid, we can find out the cold fluid outlet temperature, that is Tci plus Q upon mc dot Cpc. So this is 30 degrees Celsius plus 7600 watt upon 0.1 kg per second into 4200 joule per kg Kelvin. So this is 48.1 degrees Celsius. Okay, so now it's done, and now for the part B, determine the length required for the heat exchanger. So for part B, we just need to find out the length. So for that, we need to find first LMTDs, LMTD counter current flow. So that is del T1 minus del T2 upon ln del T1 upon del T2. So this is del T1. So del T1 is so outlet temperature we already found. So that is what, 48.1. So del T1 and del T2. So that we can easily calculate. So this is 60 minus 30 degrees Celsius minus 100 minus 48.1 degrees Celsius, and this is ln 60 minus 30 upon 100 minus 48.1 degrees Celsius, and this is degree Celsius. So this will come out to be 40.0 degrees Celsius. This is LMTD, right? Now Q is equal to overall heat transfer coefficient and the overall heat transfer area, and this is LMTD. This is LMTD safe, right? So this is area is, obviously this is the whole heat transfer area. So that is pi dn. So this is pi dl. So this L will be what? L will be Q upon U pi d delta T ln Cf. Right, now we will put every value. So this is 7600 watt. Overall heat transfer coefficient is 60 watt per meter square Kelvin into pi into 0.025 meter and 40 degrees Celsius. So this is 40.3 meter. Now We can also use NTU method. This is LMTD method. We can also use NTU method. So if you use NTU method, we need to find the heat capacity ratio. So C minimum is CH as YCH. So this comes out to be 190 watt per Kelvin. This is 0.1 kg per second into 1900 joule per kg Kelvin. Mass flow rate is same. Heat capacity, specific heat capacity is less for oil and more for water. So obviously heat capacity will be minimum for oil. And 190 watt per Kelvin, Kelvin, and maximum is 420 watt per Kelvin, right? So Q maximum is C minimum THI minus TCI. So this is 190 watt per Kelvin into 100 minus 30 Kelvin. So this will come out to be 13300 watt, right? And now effectiveness is Q upon Q max, that is actual heat upon maximum heat. So this the actual heat is what this is, this came out to be, just one second, 7600 watt. So this is 7600 upon 13300. So this will come out to be 0.571, right? Now the heat capacity ratio is C minimum upon C maximum. This will also come out to be that is minimum, this 190 upon 420. So this will come out to be 0.452. Now NTU is equal to UA upon C minimum, right? This is NTU and A is pi dl. So this is by NTU method it is already given as CR minus 1 ln epsilon minus 1 epsilon CR minus 1, right? So this CR is 0.452 minus 1 and ln 0.571 minus 1 and 0.571 into 0.452 minus 1. So L from here will come out to be 40.3 meter. Okay. So this question we are done with. We have calculated the length required by both the methods. So now we'll proceed to today's questions. These were the previous day's questions. So for the first question, a shell and tube heat exchanger is given, and there are 135 number of thin wall tubes in a double pass arrangement, and each of the tubes have 12.5 mm dia with a total surface area of 47.5 meter square. And water is flowing on the tube side, that is entering a heat exchanger at 15 degrees Celsius. There is cold fluid inlet temperature is 15 degrees Celsius, and mass flow rate is 6.5 kg per second, and is heated by exhaust gas that is entering, that is hot fluid inlet temperature is 400 degrees Celsius and mass flow rate is 5 kg per second. The gas may be assumed to have the properties of atmospheric air, right? And the properties are values are also given. Okay. And the overall heat transfer coefficient is also given as 200 watt per meter square Kelvin. The effectiveness of the shell and tube heat exchanger with one shell and any multiple of two tube passes can be expressed by the following figures. So from this we can easily calculate like the effectiveness. Easily calculate the effectiveness. So okay, so this is the intro for question number 1 to 3. So what is the first question? Choose the closest value for the gas outlet temperature. So we'll start with this question first. The gas outlet temperature, we need to find out the closest value for that. Okay, so how we will do that? First of all, NTU we can calculate. NTU, the area is already given. So from that, the calculating the minimum heat capacity, we can easily calculate the NTU, and from NTU and heat capacity ratio, we can calculate the effectiveness. And from the effectiveness, if we know, effectiveness is the heat actual heat flow to the maximum heat flow. So if we take for only the hot fluid, and the inlet temperature cold fluid is also given, so we can easily calculate the hot fluid outlet temperature, right? And from the heat balance now, the second part of the question, that is, just one second, the cold fluid outlet temperature, that also we can calculate by the heat balance, because Q we already will be knowing by that time. And then assuming fully developed flow, choose the tube side convection heat transfer coefficient. Remember that for this, first we need to find the Reynolds number, and for Reynolds number we have mass flow rate. So as here number of tubes are more than one, so we need to divide by n. That is the total number of tubes. The Reynolds number we need to divide by total number of tubes. That is mass flow rate. Actually, it is the cross-sectional flow of cross-sectional mass flow in the tubes upon the total number of tubes. Remember that for Reynolds number. And once we find the Reynolds number, we can easily use the equation for Reynolds number in tube flow, and we can find out the corresponding heat transfer coefficient. Right? So yeah, I'll give you 5 minutes for solving this. There's a question. First question, we need to find the hot fluid outlet temperature. Second question, we need to find the cold fluid outlet temperature. Third question, we need to find out the heat transfer coefficient for the tube side. Right? Just take a look at the questions. Okay, now I'll give you 5 minutes for solving this, and we'll then proceed with the solution. Uh, okay, so let us proceed with the first part of this problem. First and second part we can proceed together as well. So for question number 1 of today's class, okay. So what is said that for simplifying the diagram, it's inlet temperature of the hot fluid is 200 degrees Celsius and the outlet temperature we don't know, right? And inlet temperature of cold fluid is 15 degrees Celsius and outlet temperature we don't know. Now the mass flow rate of hot fluid is 5 kg per second and mass flow rate of cold fluid is 6.5 kg per second. It's already given. Now we'll find the heat capacity of cold fluid, that is 6.5 kg per second into 4179 joule per kg Kelvin. And for hot fluid it's so this will come out to be 27164 watt per Kelvin, and this is 5 kg per second into 1014 joule per kg Kelvin. So this will come out to be 5070 watt per Kelvin. Now CH, obviously in between these two, hot fluid heat capacity is the minimum heat capacity. This is C minimum, and now we need to find out the ratio. So this is CH upon C. So this is 5070 upon 27164. So this is 0.19. Now NTU is equal to area into overall heat transfer coefficient upon minimum heat capacity. This is 47.5 meter square into 200 watt per meter square Kelvin, upon 5070 watt per Kelvin. So this is 1.87. Now from the graph given, we will take NTU as 1.87. This will somewhat come out to be here, and we will take heat capacity ratio to be 1.19. Okay, so point heat capacity will point, this is 0.19 and NTU is 1.87. That means it will come out to be around here. This is approximately more than 0.75, so we can take 0.78. So epsilon, let us take 0.78. Now epsilon is Q actual upon Q maximum. So this is CH THI minus TH naught upon TC minimum THI minus TCI. So this is 200 minus TH naught upon 200 minus 15. So this is 0.78 and TH outlet is 55.7 degrees Celsius. This is option B. Right. Yeah. Now for the second is the cold fluid outlet temperature. So what we can do about this for question number 2? Okay, we just need to do the simple energy balance. CH THI minus TH naught is equal to CC TCI minus TC naught minus TCI. So this TC naught is equal to TCI plus CH upon CC THI minus TH naught. So this is 15 degrees Celsius plus 0.19, 200 minus 55.7 degrees Celsius. So this is 41.9 degrees Celsius. This is option. Now, for the third part is rather longer, where we need to find out the heat transfer coefficient. So I'll take you, you have not solved that yet. So I'll give you 5 more minutes, not five, 2 more minutes for solving the third part. That is the heat transfer coefficient, finding out heat transfer coefficient, and then we'll proceed with the solution. So for the third question, where we need to find out the heat transfer coefficient, first we will start with finding the Reynolds number. So as I've already said, for the mass flow rate, it will be divided by n because it is divided into n number of inlet pipes, right? Inlet tubes rather. So here n is 135. So first, this is in terms of mass flow rate, this is pi di mu. So this is total cross sectional mass flow through the total cross section upon total number of tubes, pi di mu. So this is 4 into 6.5 kg per second upon 135, that is total number of tubes, pi into 12.5 into 10 to the power minus 3 meter into 855 into 10 to the power minus 6 Newton per second meter square. So this is 5736. Now flow is fully developed and turbulent. So we can directly apply Dittus-Boelter equation. So MUDI is equal to HDI upon K. So this is 0.023 Reynolds number to the power 4 by 5, Prandtl number to the power 0.4. So for tube side, the Prandtl number is given as 5.83, 0.023, 5736, 4 upon 5, and this is 5.83 to the power 0.4. So this is 47.3. So the heat transfer coefficient is equal to Nusselt's number K by di. So that is equal to 47.3 into 0.613 watt per meter square Kelvin upon 12.5 into 10 to the power minus 3 meter. So that will come out to be 2320 watt per meter square Kelvin. This is option D. Let's find out whether this is option D or not. Yeah, this is option D. Now we are done with this question. Let us proceed to the next question. So this is the link question for question number 4 to 7. So what is said, the energy flux associated with the solar radiation incident on the outer surface of Earth's atmosphere has accurately measured and is known to be 1368 watt per meter square. So this is the heat flux, right? The diameter of the sun and earth are given, and the distance between sun and earth is also given. Now choose the closest value for emissive power of the sun. How we can do that? So applying the conservation of energy to the solar energy crossing two concentric spheres, that is solar energy that is crossing two concentric spheres, this sphere, right, that is passing through the mid section of the earth, and one having the radius of the sun. One is this concentric sphere, and another that is crossing through the mid of the earth. So by that we can easily calculate the emissive power of sun. And the acha, right. So one is like the radiation that is emitting from the sun from this circle is then incident on this sphere. From this circle it is emitting, like from this sphere it is emitting, the sphere of the sun, and from this sphere, the outer sphere that is passing to the mid of the earth, that we can clearly find by this radius between the center of the sun and the center of the earth, this RSE. So this by taking this and by subtracting the radius of the earth from that, we can clearly find out that sphere where it is incident. So by equating the emission and incident, we can clearly find out the emissive power of the sun. So let us proceed with this question first, and then we'll proceed with the next two questions, because this is a bit complicated process. Like this is the first question for radiation today. So I'll give you 2 minutes, 3 minutes rather, to solve this, and then we'll proceed with the solution. Okay. You solve this, I'll come back in 1 minute. Okay, so we'll proceed with the solution now for the first question. So what it said that the power, the emissive power of the sun from its own sphere, that is that will be emissive power, that is total emission that is being done into the surface area of the sun. That will be is equal to the the flux of the sun that is emitting from the sun, the flux that is incident on that imaginary sphere that we are seeing here, that is crossing through the middle of the earth, that will be qs, that is incident, the flux that is incident into 4 pi. First will be the radius, total radius between the sun and the earth, that is the earth, the middle of the earth, that is RSE minus uh, the radius of the earth, that is DE upon 2, right? And this is also whole square. And this is the surface area of the sun is 4 pi ds square. ds square, that is radius, radius square, 4 pi radius square, and this is equal to 4 pi ds square by 4. This 4 will cut off, this is pi ds square. Now so this will come out to be es pi ds square is equal to 4 pi rse minus de by 2 whole square qs double dash. So this is the emissive power of sun, that is 4 into 1.5 into 10 to the power 11 meter minus 0.65 into 10 to the power 7 meter whole square upon into this is the the heat flux, that is 6, the radiation flux, that is watt per 1368 watt per meter square. It's already given in the question, upon 1.39 into 10 to the power 9 meter whole square. This is the this dia of the sun. So this will come out to be 6.37 into 10 to the power 7 watt per meter square. This is which of the option? This is option D. Now for the question number 2, approximating the sun's surface as black, choose the closest value of its temperature. So if it is black body, so, then we can I'll go for directly go for the question, the solution. Okay, I'll give you 1 minute to solve this. It's not much. We just have to use one equation that you have already been taught in the class by sir. So I'll give you 1 minute to solve this. Then we'll proceed with the solution. I hope you have tried and solved it. So we'll simply use what? We'll simply use Stefan-Boltzmann equation here. So what does Stefan-Boltzmann equation say? That the rate of radiant energy emitted from a black body is sigma t to the power 4a, and per unit area it will be sigma t to the power 4. So the for calculating this for sun, its surface is black as it's already indicated. So the surface temperature will be the emissive power of sun upon sigma to the power 1 by 4. Those This is 6.37 10 to the power 7 watt per meter square upon 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So this is 1 by 4. This is 5790 Kelvin. So this is option A. Now let us proceed to the next question. At what wavelength is the spectral emission power of the sun is at maximum? So obviously here we'll use Irwin's displacement law. I'll just solve it for you, this question. So this is simply means displacement law will be using into 2898 micrometer into Kelvin. So this is a maximum is 2898 upon T. T is 5790 Kelvin. So micrometer Kelvin. So Kelvin will cut off, and this will be 0.50 micrometer. This is option B. For question number 7. Assuming Earth's surface to be black and the sun to be only source of energy for the Earth, estimate the Earth's surface temperature that we need to find out. So now, first of all, same way what we have done for the sun, in case of sun, we'll do what? We'll do the energy balance on the surface of the Earth. So if we will do the energy irradiated on the surface is QS double dash on the that multiplied by the projection area, like we'll consider like when it will be projected on the Earth, it will be projected on only the spherical, like circular surface cross section, right? Only this circular surface cross section, not on the whole sphere. So it will be on the circular cross section, it will be irradiated. So we'll be taking that area, and this will be equal to the energy emitted by Earth. Earth will also emit some energy, right? So if we will consider that Earth to be black, so it will be the energy emitted will be emissive power of Earth multiplied by its total surface area. So because it will be irradiated in all the surface, like whole surface, right? In everywhere. So if we will do that, and then we will get the emissive power from there of Earth, and then that will be for black body, considering Earth to be black body, this will be sigma t to the power t, Earth to be to the power 4. So from that we can get the temperature. So I'll solve that for you right away, because it's already 9, and we have many more questions left. So I don't think I'll be able to solve all of them today, but we'll try to solve max. So first, the radiation that is falling on Earth, considering the circular cross section, the projection area basically, and this is the emission of Earth. This is square. This is the sphere, considering Earth to be a sphere, like Earth is sphere, right? So this is the radius of Earth. So the whole surface area of the Earth. So this is E into 4, pi d E square. Just 1 second. Yeah. So now considering R to be a black body, this is sigma t to the power 4, right? So now this we can write as QS double dash 4 is equal to sigma t to the power 4, or the temperature of the Earth is equal to is equal to QS double dash upon 4 sigma to the power 1 by 4. That is 1368 to the watt per meter square upon 4 into 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4 to the power 1 by 4, and this is 279 Kelvin. This is which option? This is option D. Right, so this is done. Now, let us proceed to the next question. What is said that a dark surface of ceramic stove top may be approximated as a black body. The burners, which are integral form of stove top, are heated from below by electrical heater resistance. So, properties are given, and it's given that the heat transfer coefficient, the Nusselt's number is related to Rayleigh's number by this, and Rayleigh's number is given as this. So considering burner diameter to be 200 mm, operating at uniform surface temperature to 50 degrees Celsius and ambient air temperature is 20 degrees Celsius. Without a pot or pan on the burner, calculate the rate of heat loss by radiation and convection. We can do that and choose the closest value. So solve this. I'll take I'll give you 2 minutes for this, and then we'll proceed to the solution because we don't have much time left. Yeah, because we don't have much time left. So okay, no one is the class as it is, so it's already recorded. The voice is already recorded. Yeah, so I'll give you 2 minutes to solve this and then we'll proceed with the solution. Okay. Okay, we'll proceed with the solution then. So for question number 8, both 8 and 9 are involved in this, right? So first we'll do a simplified diagram of this. So we'll do a simplified diagram of this. So what we'll do? So this is the surface of the burner, and this is the resistance heater that is placed at bottom, right? And this electricity is applied here, and now here on one end there will be radiation loss, and on one end there will be convection loss. So there is air, and on both of the surface, okay, so the surface temperature is 250 degrees Celsius, and this is ambient temperature is 20 degrees Celsius. This dia is 0.20 meter, that's 20 centimeter. Okay, now first for the radiation loss, this will be area of surface into as it is considered as a black body, so it's emissivity power. So this is pi d square by 4 into 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4 into temperature difference, like 523 T to the power 4, that is surface temperature to the power 4. Surface temperature is given as 250 degrees Celsius, so 250 plus 273 to the power 4, as this is in Kelvin. So this will be 133 watt. And now for the convective loss, we need to find the characteristic length. So the characteristic length is area of the surface upon the perimeter, right? So this is pi d square upon 4 upon pi d, right? So this will come out to be d upon 4, this is 0.05. Now Rayleigh's number is equal to g beta ts minus t infinity L cube upon alpha nu. So this will come out to be 9.8 meter per second square into 0.00245 Kelvin inverse, this is beta, into 250 minus ambient temperature is 20 into 0.05 meter whole cube, this is the L, the characteristic length, upon alpha is 27.4 into 10 to the power minus 6 meter square per second, and nu is 39.7 into 10 to the power minus 6 meter square per second. So all this, calculating all this, will come out to be 6.35 into 10 to the power 5, right? So now this is Nusselt's number. Now H is equal to Nusselt's number K by L. So this is 0.54 Rayleigh number 1 by 4 K by L, right? So this will 0.54 into 6.35 into 10 to the power 5 whole to the power 1 by 4 into 0.0344 watt per meter Kelvin upon 0.05 meter. So this is 10.5 watt per meter square Kelvin. Now the convective heat loss is equal to h bar as Ts minus T infinity. This is equal to 10.5 watt per meter square Kelvin into pi into 0.2 meter whole square upon 4 into 250 minus 20. So this will like come out to be 75.7 watt. So if we go on to the option, this is 133 and 75.7, that is 76 is option C. Sorry, A. Yeah, option A. Now for question number 9, if the efficiency associated with energy transfer from heaters to burners is 90%, choose the closest estimate of the electric power required. So yes, we know the total heat loss. We'll just add that up to find the total heat loss. That is convective and radiative, and upon the efficiency we'll give the total electric power required. So that is only required to transfer the power to heat loss. I'll give you 30 seconds to solve this, and then we'll proceed with the solution. We will take 5 more minutes to end the class, and by that time we'll solve one more question, and I have 3 more questions left, right? Like 4 more questions. One question will solve, and another 3 questions I'll give you as homework. Okay, let us proceed with the solution then. So this is question number 9. So efficiency is given as 90%, and as I've already said, the power, total electrical power that is required uh, will be the total radiation loss and convective loss, that is the total loss, heat loss, upon the efficiency. That is 133 plus 75.7 watt upon 0.9. So that is 232 watt. Now for question number 10, let us proceed to question number 10. This is the last question for today. Rest 3 questions I'll give you as homework. 3, no, I have 4 more questions, I guess. Yeah. Yes, I have 4 more questions. I'll give you that as homework. So this is just a spectral distribution of the surface irradiation, that is G, that we have learned about in the class. And what we want to know? We want to know the total irradiation. Just take out the area under the curve, and then we'll get the total irradiation. Okay, I'll give you 1 minute to solve this, and then we'll proceed with the solution, because it's already 9:40, right? Okay. Okay, I think we should proceed with the solution. So, okay, so this question number 10. So the total irradiation may be obtained as follows. So, uh, how do we do that? Just this is area under the curve. So this is 0 to infinity. As we already know, this is g lambda d lambda monochromatic. So this is 0 to 5 micrometer. There is one trend of graph. So this is d lambda g lambda d lambda plus from 5 to 20 there is one trend of graph. 5 to 20 there is one trend of graph, g lambda d lambda plus from 20 to 25 there is one trend of graph, and from 25 to infinity there is one trend of graph, right? So from 0 to 5 there is this is a triangle, so this is half into length into breadth. So this is half into length, that is 1000 watt per meter square micrometer into 5 minus 0 micrometer, right? Plus then it is a rectangle, so this is 1000 watt per meter square micrometer into 20 minus 5 micrometer. Now the next one is also the same, half into 1000 watt per meter square micrometer into 25 minus 20 micrometer plus 0. So this is 2500 plus 15,000. No, there is nothing under the curve, right? On the last part. That's why 0. 2500 watt per meter square. So this is to 20,000 watt per meter square. Yeah. So it's done. 20,000. So, okay, we don't have much time left now. So I'll close the session for today. I'll show you the next 4 questions, and I hope you will try this out at home, and we'll discuss about this in the next class. So this is the first question. I won't discuss today about this because we don't have much time left. It's already 9:20. This is information that is related to first question. You take the screenshot of both of them, or you can also check out the recording. You will use this to solve this question. And another question is also there, over there also you can use this information. There's the equation that you need to use, like not equation, rather there's the fraction, how it is related to emissive power, it's given here, and how you can use this. This question number 12, this question number 13, this question number 14. Okay, so I'll end the class here. So just 1 second. 11, 12, 13 and 14 we'll do on the next class. Okay, so today no one was present, so I'm marking everyone to be absent today. This recording will be uploaded in YouTube section, and the link also will be provided to you. And the question PPT will also be shared, so that you can access to that, and also you solve the 4 questions that I've left for homework, and we'll discuss in the next class. Thank you. I'll meet you guys next week. But today it was a change of schedule because I was not available on Tuesday. and next week I'll be available on the regular Tuesday time from 7 to 9. Okay, bye guys.